So in this video, we're diving in the GPUs. Up to now, our discussion has been focused on the high-level organization of our model operations. We've moved around computations on accelerators, taking into account general memory constraints and high-level scheduling of compute units. But this section will dive into much more detail on GPU architecture, and in particular, NVIDIA's GPU architecture, since that is the largest provider of GPUs by far. But the general ideas as often can be reused on similar accelerating units. So we're talking about TPU 5, Trainium on Amazon, even though the information available around these accelerators is much, much smaller, and it's more tacit knowledge that is held by few experts in frontier labs that are really applying these. But enough for that aside, and we'll briefly explain how GPUs are organized before covering the flash attention revolution, how to efficiently schedule workload on a GPU, and finally explain how various positions can be efficiently used on GPUs. So we're talking about like BF16, float 16, float 32, and I think they get into 8-bit or 1-byte quantization as well. So GPUs are a very hierarchical compute device, and when we talk about compute, it consists of an array of compute units called SMs, or streaming multiprocessors, with each streaming multiprocessor containing and controlling a set of streaming processors, also known as cores. That's why we have a multiprocessor, because it has multiple processors, aka cores. For example, an NVIDIA H100 GPU has 132 streaming multiprocessors, and per SM, 128 cores, resulting in 16,896 cores, with each core capable of handling multiple threads simultaneously. So if we look at this image, we have our global memory, which is the value you get when you look at VRAM. So if you have like a B200 GPU, the latest Blackwell architecture, data center grade NVIDIA GPU, it has 200 gigabytes of VRAM, as the name suggests, and that is the global memory value. And then you have the load and store, which handles reads and writes from the global memory to the different devices. And then you have the device memory, which is much faster. In fact, if we go here, it's 7 times faster than global memory in terms of transfer speed. So, of course, per device, it's easier, since it's not shared memory, to have faster communication. And then on the actual GPUs, let me just read what it says. The memory side is hierarchical with several layers of cache and memory. So registers are the smallest units and are private to the threads during execution. Shared memory and L1 cache are shared between the threads running on a single stream multiprocessor. Higher up is the L2 cache, which is here, shared by all stream multiprocessors. Finally, there's the global memory, which is the largest memory on the GPU. And as I mentioned, for example, if you have H100, then that would be 80 gigabytes, but it's also the slowest to access and query. So registers, the smallest units, and are private only to thread during executions right here. Then the shared memory and L1 cache are within the device, shared between the threads running on a single stream multiprocessor. And then the L2 cache, which is here, is shared by all stream multiprocessors. And then we have the global memory. So this is kind of a higher level look at the SMs and how they interact with global memory. And then this is more low level, because we're breaking down the memory hierarchy into the cores themselves and the register. The goal of GPUs are to run as many workloads as possible, in essence parallelization, by taking advantage of the hierarchical organization of computation and memory. So this comes back to the theme of overlapping computation communication, which we discussed quite in excess throughout the parallelism section. Next, a piece of code running on a core of the GPU is called a kernel, and this can be done in languages such as CUDA or Triton, CUDA being in C++. I mean, it is its own language, but it's essentially C++, and then Triton, which is in Python. So it's kind of like a high-level CUDA programming language with less customizability or less ability to mess up memory, but then also, since you can't really mess up memory stuff, it's less difficult to mess it up. But if you're an expert, then of course you'd want to use CUDA, because you can essentially move memory around to quite a precise level. And then there's also PTX, which is the low-level assembly used by NVIDIA GPUs themselves, so parallel thread execution. And I've heard that DeepSeek was coding in PTX in order to have the most optimized, thread and memory allocation with their latest models, so V3 and R1. And once you have a kernel, you need a specific part of code called host code right here, which is run on the CPU. I don't know what else you would have other than the CPU to host the code. And it takes care of preparing data allocations and loading data onto code. And then you have the other section, which is the device code run on the GPU itself. So on the CPU, we can see that we're initializing the size of float so that we have the correct size and memory that we're allocating. And then we will get 3 pointers, A, B being what we're adding, what we're adding together, and then the sum would be C. And we are allocating the size that we've pre-computed here. And then we copy vectors from host memory to device memory so that it's on the GPU because we're doing the computation on the GPU. And then you start a kernel, complete the add, and then copy the result from device memory to host memory. And then we have our answer, and we have to free our memory afterwards because there's no garbage collector in C. So you have to do this on your own. Of course, this gives a lot of ability to kind of customize once, like I said, but ability also to screw things up. And kernels are generally scheduled as follow. So threads are grouped into warps of size 32. So 32 threads equals 1 warp. And all the threads in a warp are synchronized to execute instructions simultaneously, but on different parts of the data. Warps are grouped in larger blocks of more flexible size. For example, 256, but this can vary, with each block still being assigned to a single stream multiprocessor. And a stream multiprocessor may run several blocks in parallel. However, depending on the resources, not all blocks may get assigned for execution immediately. Some can be waitlisted, waiting for resources. And this type of scheduling happens within the GPU. So this is not something, at least unless you're at the very lowest of levels, that you would have to schedule yourself. The main thing to remember from these details is that there are various sizing and allocation constraints. For example, the size of memories, number of current blocks and threads in the warps, and that's spelled incorrectly, wraps, which need to be taken into account to use the GPU architecture in the most efficient way. And how can we improve performance with kernels? If you're looking to add a new operation that lacks an optimized kernel, so of course there are many kernels available because the GPU operations that we do on a day-to-day basis are optimized essentially to the limit because, well, these are like operations that are happening trillions of times per day probably. So there are many people that have worked on optimizing these already. But if there's a new type of operation that you want that doesn't have an optimized kernel, or to speed up an existing PyTorch function, so that there could be PyTorch functions which are not as optimized as they could be, writing kernels from scratch might seem like the most direct route. However, creating high-performance CUDA kernels from scratch requires extensive experience, domain experience, tacit knowledge, and a steep learning curve. So the better way to get started is to leverage torch.compile, which dynamically optimizes PyTorch code by capturing your operations and generating lower-level, high-performance kernels in Triton. So let's say we have this activation function called the exponential linear unit, which if x is greater than or equal to 0 is essentially just a ReLU, so it's x itself. But then if it's less than or equal to 0, it's exponential of x minus 1. And you can start by a simple PyTorch implementation, which is just literally if x is less than 0, we do torch exponential of x minus 1. If not, it's x, and ignore the alpha because it's just equal to 1. And this is essentially the simple torch implementation. But if you do add this at torch compile above the function definition, then you will have a large difference between the compiled and non-compiled versions, which is evident here of the comparison of the two, implementations of this activation function. So for a given input size n, we have the gigabytes per second, so I guess the throughput of the function. And with torch compile, it's, from 500 to 3000. So it gets up to 6 times faster depending on the input size. However, if this performance increase is insufficient, you can consider implementing Triton kernels themselves. This is like one level above implementing a CUDA kernel. And as a starting point, you can actually see the Triton kernel generated by torch compile. To do so, you just need to set the environment variable torch logs to output code. And once you run the script with the torch.compile decorator, it generates and outputs the corresponding Triton kernel, which is in this case the following function. But we can also they made this more readable with a thorough amount of comments. So we have the exponential linear unit, or is that what it's called? ELU, exponential linear unit function. And we have our input pointer, output pointer, number of elements, block size, etc. So the first thing we do is calculate the starting index for this block and then create an array of indices for this block. So we have our memory, but you don't actually need to do the memory allocation itself. I guess it's happening in an abstracted layer, since this is not as low level as CUDA. Then we create a mask to ensure only valid indices are processed via this operation, block indices less than number of elements. Then we load input values from the input pointer based on valid indices, define the exponential linear unit parameters. This is the threshold for LU activation, in essence, if x is greater than or less than 0. Then we have a negative max. I'm not entirely sure what this represents, but then we have our exponential value. Define the output shift. So this is just subtracting by 1. And then we have our output. So store the computed output values back to the output pointer is this command here, tl store. And this is what actually does the calculation. And here, tl.programID0 provides a unique block ID, which is at the very start, that we use to determine which section of data that block will process. Using this block ID, block start calculates the starting index for each block section, while block indices specifies the range of indices within that section. A valid mask ensures that only indices within number of elements are processed, safely loading the data with tl load. And the elu function is then applied, modifying values based on whether they're negative and resulting in a memory in the memory it's being written to tl store. And if you benchmark the Triton testing benchmark just as it was generated by torch.compile versus just the torch.compile decorated version, the standalone kernel is superior with smaller sizes, and this is just likely to the compilation time of torch.compile. So if you're dealing with smaller input sizes, then you could just get the Triton kernel generated by torch.compile and use that out of the box. But even in Triton, we cannot fully achieve sometimes the peak performance on the device due to language limitations, such as handling low-level details like shared memory and scheduling within streaming multiprocessors. Triton capabilities are therefore restricted to blocks and scheduling of blocks across SMs, but not within. To get an even deeper control, however, you can use CUDA to implement kernels directly with capabilities such as memory management within an SM, and we will be discussing this in the next episode. So thanks for watching, and see you then.